Hello everyone, this is the video lecture of section 8.1 part 1. Okay, chapter 8, we're going to study sequence and series. Sequence and series. This case, section 8.1 is about sequence. You already learned sequence even starting from algebra 2. Let's say a sequence is a list of numbers written in a row, right? From the first, second, third, we call it, if I name this sequence as A, the first term of sequence A will be A1. This is A2, A3, A4, all right? And what would be AN? Well, if you think about it, this is an arithmetic sequence. You already learned 3n plus minus 2, right? Because you have a common difference 3, you will have 3n minus 2. Okay. Of course, the rigorous definition of sequence is you can write this one as just like f of x equals 3x minus 2. If you think of this one as a function, your inputs are consecutive integers, right? And your output is a real number. So sequence can be defined as a function whose domain is a set of consecutive integers, okay? If the domain is finite, so if you have only finite number of terms, then we call it finite sequence. If you have infinite many terms, we call it infinite sequence. In order to denote the whole sequence, one way to do that is just list, something like this. Then we know the pattern from the first few terms, or just write it AN. This means the whole sequence, all right? Or sometimes we write it starting from 1 to infinity. Usually our sequence starts from 1, sometimes from 0. N equals 0, mostly. So, example on A. So, if you have this, that means your nth term, n over n plus 1. So if you write it for few terms, n equals 1, 1 half, n equals 2, 2/3, 3/4, and so forth. Okay? Now, second, what if you have minus 2/3 to the nth power? Okay, so that means your general term, nth term is minus 2/3 to the nth power. N equals 1, negative 2/3. N equals 2, square, 4, 9. Negative 8 over 27. 16 over 81. Keep going. Right? Or, you have 2n plus 1. N runs from 1 to infinity. 2n plus 1. N equals 1, 3, 5, 7, 9. Okay? D. 1 minus negative 1 to the nth. N equals 1 to infinity. 1 minus negative 1 to the nth. 2, 0, 2, 0. Okay? Now, quite often you will see that minus 1 to the nth. This is when n equals 1, minus 1 to the 1 power is negative 1. Negative 1 to the square, square is 1. So that's why 1 minus 1 is 0. N equals negative 3, negative 1 to the third power is negative 1. So this is up, bouncing between negative 1 and 1. Adding 1 make it between 0 and 2. Now, negative 1 to the nth can be written as n pi. Because cosine pi is negative 1, cosine 2 pi is positive 1, cosine 3 pi negative 1, cosine 4 pi is positive 1. So behave just same as minus 1 to the nth. Now, you might think that your all sequence have always this kind of formula. Well, you might not have such obvious formula. Let's say your sequence is can you guess the rule of this? It will be extremely hard. There's no explicit formula here because this is decimals. Decimals of pi equals 1.41596. Keep going. Okay? This is pi is irrational number. Irrational number, that means there's no repetition here, no explicit rule. Okay? So, you may not have some explicit formula for A, but of course, all the sequence we are dealing with here, the interesting ones in homework problems or quiz or exams are all of them have some formula, or at least recursive formula. You will see what recursive formula means. Actually, the next thing. So this is what we call explicit form or functional form, just like function formula, right? Instead of actually of n. There are other ways to describe sequence, also very important one. Example 2, recursive relations. For example, a1 equals 1, an plus 1 equals 1 over 1 plus an. So this one gives you the relations between two consecutive terms. So if you know nth term, then you can calculate the next term, an plus 1. Okay? Now you know a1. Then you can get a2 equals what? 1 over 1 plus a1. So 1 over 1 plus 1, 1 half, right? a3, 1 over 1 plus a2. 1 over 1 plus 1 half. 3 over 2, 2/3, right? And then a4, a3, 2/3, which is 5 over 3, so 3 over 5. So you can go forever. So, in this case, you can get any term, like 800, if you go through this, right? Unlike here, you just plug in 100 to get 800. Here you have to go through like 100 steps or 99 steps. So it's not as convenient as explicit relation, explicit expression, but it's still much better than nothing, right? Or f1 equals 1, f2 equals 1, and f of n equals f of n minus 1, n minus 2. N is greater than 3. Starting from third term, it is always sum of the previous two terms. Previous term, two previous terms, right? Two previous terms, sum. Now, then once you have f1 and f2, you can get f of 3 as f of 2 plus f of 1 plus 1 plus 1 equals 2. F of 4 n equals 4. two previous terms. 2 plus 1 is 3, right? F of 5, f of 4 plus f of 3. F of 4 is 3. And the next term is just adding these two, right? Keep going. 13, and so forth. This is a very famous sequence. It's called Fibonacci sequence. Okay? Alright. As I said, this is a function. The graph of this is a line. Because x can be any real number, so corresponding point x versus 3x minus 2. If you plot this one for all x, x can be any real number, it'll make a line. On the other hand, if you have graph of this sequence, y equals an will be y equals 3n minus 2. It's not entire line. It only for integers, right? When n equals 1. So it'll be only integer dots. 1, 1, 2, 5, 3, 8, 3, 7, 1, 1, 2, 4, yeah, 2, 4, and 3, 7. These dotted discrete points on this line. Okay? The graph of a sequence. Think about graph of this sequence. N plus 1 over n. If you split n over n plus 1 over n, you can write 1 plus 1 over n. So that would be n equals 1, 2, and 2/3, and 3/4. No. N equals to 3 over 2, 4 over 3, 5 over 4, 6 over 5. Right? 101 over 100. Keep going. So if you draw the graph, what would you see? 2 over here, 1 over here, at 1, 2, at 2, 1.5, at 3, 1.333, at 4, 1.25. If I draw y equals 1 line, this is 1 plus 1 over n. So when n equals 3, 1 plus 1/3. 1/3 above 1. 1/4 above 1. 1/5 above 1, right? And 1/6 above 1. So you know that these things are getting smaller, right? And smaller. So what do you expect? As n goes, getting larger and larger, this thing will be approaching value 1. Because obviously 1 over n will approach 0. So, in that case we write it, limit of this sequence. N over, n plus 1 over n equals 1. Just like the limit of x plus 1 over x as x going to infinity equals 1. Just like that. As n getting larger and larger, this one is indefinitely getting close to 1. Okay? So, let me check the recording before we continue. Okay. Here, next one. So let me give you in general sequence AN has the limit L or converges to L as n goes to infinity. Well, we don't even have to write it. And denote it and write as limit n goes to infinity of an equals L, or we say that an approaches L as n goes to infinity. Okay? If and only if an value and L is getting can be as small as we like, for all sufficiently large n. Okay? If we can make this one as small as we want, as close to 0 as we want, for all sufficient large, for all n greater than certain value, for all sufficient large n value, we can make this one as small as we want, as we can. Then we say limit of sequence an equals L. Okay? First. Second, if a sequence does not have a limit, then the sequence is set to diverge. Not having limit means diverge. Well, English word diverge is like you're getting farther apart. But in sequence, diverge can be anything other than convergence. For example, we'll see some examples. So example 3. Investigate convergence of the sequence and A. Investigate the convergence of the following sequence. First of all, an equals n over n plus 1. B, an equals n squared. C, okay, let's consider convergence of these three sequences. Okay, so here, A. Now, an is n plus 1 minus 1 over, I can write it this way, and split. 1 minus 1 over n plus 1. What do you think? Obviously, 1 over growing number is getting a little smaller and smaller. It's almost 1 minus almost 0. Just getting closer and closer to 1 from below, right? So in this case, limit of n over n plus 1 is 1, obvious. It is convergence sequence. B, n equals n squared, 1, 4, 9, 16. It's getting bigger and bigger, quadratic function, quadratically fast. There's no way this one approaches anything. So it's diverges, right? You can say that diverges. Getting larger and larger, without bounds, it's growing. In that case, even though it is divergent, we use this notation. It doesn't mean that your limit is infinity. Infinity is not a limit. It diverges. It doesn't have a limit. Yet we use this notation, limit of n squared as n goes to infinity as, this is supposed to be limit value. Now we are using this notation even though there is no limit. So this is in a sense the abusive usage of the notation, right? Abusive notation. Abusive use of notation, whatever you call it. So we accept this, all right, because it is convenient. So if you are asked if there is a limit for this sequence, then your answer has to be no, there is no limit because it is divergent sequence. But if you are asked to fill up this blank, then you can put infinity sign. Understanding that infinity is not a limit value. This is not even a real number. Your limit has to be a real number, finite real number. Okay? But still we allow this notation. Third, minus 1 to the nth. So if n starts from 1, minus 1 to the odd power 1, negative 1, 1, negative 1, 1. It is oscillate between 1 and negative 1, right? In English, we don't call it diverge. It's oscillate between two numbers. Well, limit of this one does not exist. Does not exist. It stands for does not exist. We don't call it plus minus 1. Okay? Limit has to be one target number you approach, getting closer and closer, rather, right? You can't have two different numbers, all right, for a limit. Okay? Limit does not exist. Don't say equal. It's not equal. This is a sentence. Limit of this one does not exist. Or you can say that this limit, an diverges. See? As I said, in English, diverge means that you are getting farther away from each other, farther away from something. It's not getting farther away. So, in mathematics sequence, divergence means anything other than convergence, right? Even if it's not really getting farther away from something. As long as it is not convergent, we call it divergence or divergent. Okay? Now, in comparison with this, in calculus 1 you learn that when you have the same degree, degree 1 and degree 1, what did you do? You divide both sides by highest power of the denominator. Then you get 1 over 1 plus 1 over x, x going to infinity. This one approaches 0. So 1. Just like this, right? Think about it. If you draw the graph of this one as a function of x, this one will be going like this. So which is 1. This is the graph of this, okay? And if the function f of x equals x over x plus 1 approaches 1 as x going to infinity. Now, your sequence, this one is just as discrete points corresponding to integer x values. If the whole graph approaches some value, then these red dots are forced to converge to the same value, isn't it? So if this one, if you call it this is f of x, this is just that function's value at integer n. So it's I will call it this is mother function. if the mother function approaches something, then the derived sequence from that mother function will be converging to the same value. Make sense? It's obvious if you really think about it. So we have the following theorem. So theorem 1. If limit of f of x as x approaches infinity is L, and an equals f of n for all n, 1, 2, 3, forever, then limit of f of n, an. If your mother function approaches n, your derived sequence definitely approaches the same value. Okay? Then remark. Remember that x going to infinity. Limit of 1 over x to the r as x going to infinity equals 0 if r is greater than 0. Like 1 over x squared, or 1 over actually 1/2 square root of x. As long as this power is greater than 0, positive power, then as x going to infinity, your denominator goes to infinity. Therefore, 1 over a really large number goes to 0, right? We know this. Therefore, according to this theorem, limit of 1 over n to the r power as n goes to infinity will be 0 if r is positive. Okay? So 1 over n squared, 1 over n to the 1/2, 1 over cube root to f, 1 over n to the 100 power, all going to 0 as n going to infinity. Alright. Then we have following properties, just like the limit properties in function limit in calculus 1. You have a limit properties following. Okay, let me check recording. Okay. So here, theorem. If limit of an, n goes to infinity equals L, and limit of bn, k, and c is a real number, then first, an plus or minus bn equals L plus or minus k. Limit n goes to infinity, c times an, c times L. Okay? And limit n goes to infinity, an times bn will be L times k. So I'm going to explain after I write everything here. If k is not 0, I'm going to write something here. 5 L to the p. P is positive. Okay. All right. Now think about it. This means that if n is very large, sufficiently large number, an is almost L, bn is almost k. So an plus bn will be almost L plus k, isn't it? Right? Almost L value minus almost k value will be almost L minus k. almost L times C will be very close to CL, almost CL. Almost L value times almost K value will be almost L times K. Almost L over almost K will be almost L over K. Almost L to the P power will be very close to L to the P power. So this one really makes sense. Now if you rewrite L equals this, what can you say? You can split limit operation over addition and subtraction. Constant C times L, which is limit at AN. Constant multiple can be taken out of the limit operation. And your limit operation also can be split over multiplication too. Or division. Okay? Or even power function. Okay? Just like the function limit. We have the same thing. Limit of f of x equals L as x approaches C. Limit of g of x equals k as x approaches C. Then f of x plus minus g of x limit as x approaches C will be same as this, right? It's exactly the same kind of properties. And also you have the squeeze theorem too. Just like before. Just like calculus 3. Squeeze theorem. That is, if AN, BN, CN in that order, for all n greater than some number, it doesn't have to be that way from the very beginning. After certain term and on, always 3 sequence has this order. BN is always between AN and BN. For some positive integer. And somehow the lower sequence, smaller sequence, approaches some number L, and your upper sequence also approaches the same value. So sequence AN is converges to L, sequence, AN, sequence CN, lower sequence, upper sequence, both approaches L. Both approaches L. And your sequence is in between. BN is somewhere in between. If upper one and lower one approaches the same value, your middle one is forced, squeezed, to converge to the same value. Right? Squeezed here. Then the middle sequence must converge to the same value. Okay? This is squeeze theorem. The first application of squeeze theorem will be also very obvious one. That is, we call it corollary. CR means corollary. Corollary for if limit of absolute value of ANs, our sequence is absolute value of other sequence. Absolute value of AN equals 0. Then AN must be 0, of course. How do we prove that? Proof. Okay, AN is always less than equal to absolute value of Fn, but greater than equal to minus of absolute value of Fn. Absolute value of AN. It's kind of misleading. It looks like AN is somewhere in the middle. No, AN will be always either same as this or same as this. If AN is positive, same as this absolute value. If AN is negative value, it will be same as negative of absolute value. If it's negative 3, negative of absolute value of negative 3 is 3. So negative 3 equal to this. Okay? But anyway, still, for all n, because it is 0, minus of AN, we just want the negative 1 times absolute value of n. Constant multiple can be taken out of minus 1. Right? We learned that this is already 0. Suppose this is 0. 0. And obviously, that is same as this. So both lower sequence approaches 0, upper sequence approach the same value 0. Therefore, by squeeze theorem, the middle sequence an must be converging to the same value 0. Okay? Alright. Now, let me silence my computer. Okay. Now, example 5. Find the limit of an n goes to infinity if it exists. Okay? A sine of n over n. B 2n plus 1 over C a n equals 2n plus 1 over this. Okay? Let's say 3. Why not? D a n equals n over e to the n. E 2 to the n over n factorial. Okay, let's do this. So A. Now sine n over n. Okay, sine n. If you take up as sine of n over n absolute value of sine of n over absolute value of n is just n, right? But sine of anything absolute value is always less than or equal to 1. So it's less than or equal to 1 over. Alright? Obviously this is absolute value whatever of greater than or equal to 0. Now, limit of upper sequence 1 over n is approaching 0. Limit of your lower sequence, which is constant sequence. You can consider this constant sequence. Therefore, this middle one, by squeeze theorem, limit of absolute value of sine of n over n equals same value 0. Now, from this, that means from that corollary, inside one equals 0. Okay? Now, you could have done this way, actually. Sine of n is between -1 and 1. Divide both sides, all sides by n, then what do you get? So sine of n over n is between -1 over n and 1 over n. This one approaches 0, this one is also approaches 0, therefore by squeeze theorem, the middle sequence will approach 0. Again, squeeze theorem, alright? This one was also squeeze theorem, this one was squeeze theorem. So squeeze theorem was crucial here. What about B? B a equals 2n plus 1 over 3n plus 1 minus 1. Okay? The same thing. If you divide both numerator and denominator by the highest power of the denominator, which is n, what is it? 2 plus 1 over n, 3 minus 1 over n. That one approaches, this one approaches 0, this one approaches 0. It's 2/3. So it's just like a 2x plus 1 over 3x minus 1 when you have the same degree numerator and denominator as x going to infinity or negative infinity. Your limit will be just ratio of the common ratio of the leading coefficient, right? C. What about Bn? 2n plus 3n squared. I'm gonna just write it this way. Not limit n goes to infinity. 2n plus 1 over 3n squared plus n plus 1. Again, that is equal to, I'm trying to write down every single step here. Then n goes to infinity. If you distribute 2 plus 1 over n, distribute n, 1, 3n, 1, 1 over n. What do you see? This one approaches 0, approaches 0. I'm sorry. We have to divide by highest power of the denominator, n squared. N squared. Sorry about that. Then you get 2 over n, 1 over n squared over 3 plus 1 over n, 1 over n squared. This one approaches 0, approaches 0, approaches 0, approaches almost 0 over almost 3. Yeah, that is 0. This is what happens when your denominator has the highest power, bigger than the highest power of the numerator. So in polynomial case, that means degree of the denominator is greater than the degree of numerator. Then you get you approaches 0. You approach 0. Okay, the next one, D. Now, if I define f of x, let f of x be x over e to the x, then our an is nothing but f of n. So instead of finding limit of this sequence, I'm going to find the limit of this mother function. Because then when you have dealing with function infinity over infinity form, we can use L'Hopital's theorem. L'Hopital's theorem. So derivative 1, derivative still 1 over very large number becomes 0, because this is 0 over infinity style, right? So 1 over. So finite number over getting larger and larger indefinitely, so it's going to approach 0. Therefore, from the previous theorem, what was it? Theorem 2? Was it theorem? No, theorem 1. According to theorem 1, this derived sequence will be also approaching 0. Now note, don't do this. Many students write this. Infinity over infinity. So I'm going to use L'Hopital's theorem. So derivative of n equals 1. Derivative of e to the n is e to the n. Hey, 1 over infinity form, so 0. Strictly speaking, this is wrong. This is not differential function. This is defined only at integers, right? It's not even defined over a real line. This is a discrete function. How can you make derivative, right? Even though you're writing n, you are treating n as like real variable x, not integer n. So strictly speaking, this is wrong. You have to apply L'Hopital's theorem to mother function x over e to the x, not to the sequence. You cannot apply L'Hopital's rule to sequence. So if you write something like this in quiz or exam, you're going to lose substantial points because you have been warned. Okay? All right. And finally, okay, A1 is 2 over 1, A2, 4 over 2, A3, 8 over 3 factor is 6, a 4, 24, right? 4 factorial, 5 factorial, 120, 32. It's getting smaller, but it's hard to know which number this one converges, or even converges to 0. Here, exponential function 2 to the n grows fast. And factorial also grows fast. 1 factor is 1, 2 factor is 2, 3 factor is 6, 24, 120, 720. It grows very fast too. So the limit value of this one will be determined by which one grows to infinity faster. Okay? If the denominator grows much faster than this, incomparably faster, then it goes to 0. If 2 to the n goes much faster than this, it can go to infinity. Or they can approach some finite real number. Who knows? Okay, so now, if n is larger than 4 or 3, you can write it an as now 2, 2, 2. Multiplying 2 by itself by the n factors, 1, 2, 3, all the way to n. I can write it separated first term, and then middle terms. No. This is 2 times the last term. Okay? Then, what do you see? This one, 2, 3, 4, right? This is keep multiplying by 2. Look at this. 2 over 2, 2 over 3, 2 over 4. Always less than 1, less than 1. Overall, this is less than 1. Strictly less than 1, right? This is 4 over n times something less than 1. So definitely less than 4 over n, right? So your an, obviously, your an is positive. Less than equal to 4 over n. Okay? And then your upper sequence, 4 over n, approaches 0. And obviously your lower sequence, constant sequence 0, also approaches 0. So by squeeze theorem, your middle sequence, which is 2 to the nth over n factorial, approaches 0. Okay? Turns out that n factorial is growing much faster than 2 to the nth. Look at this. 2 to the nth is always multiplied by 2. Always multiplied by 2 each time. n factorial is multiplying by growing number, right? So definitely your n factorial will be much larger than the mighty exponential function. Okay? So n factorial is even larger than exponential function with base greater than 1. Okay? Alright. Now this is the end of the part 1 of the, toward the end of the part 1 of section 8.1. That is, a remark. Recall that x going to infinity, r to the x, remember? Infinity. 0. If absolute value r less than 1. If r equals 1, then does not exist otherwise. Right? Now, let's integer power. If you have a rational power, irrational power, when you have a negative r, it's kind of, let's see. Actually, you learn this one in math analysis or pre-calculus, right? If your base is between -1 and 1, which means -1 and 1, the higher power means smaller, getting closer, like a 1/2 to the 10th power, right? Or -1/2 to the, right? Same. 11 will be negative, but very even, absolutely even closer to 0. So it's going to 0, right? So knowing this, example 6, A, limit as n goes to infinity, 1/2 to the nth power equals 0. -2/3 to the nth power, also 0, because both of them, the base, absolute value of the base is less than 1. Okay? If -1 to the nth, we saw that +1 -1, so does not exist. Anything other than these two. Alright? Limit of 3 to the nth does not exist. Or you can write it this way. That's fine. But limit does not exist. Okay? So the first part 1 of section 8.1 ends here. Alright? You have another part, second part of section 8.1. I'll see you then. Bye.